Okay, this will be the second type of example, or the third type, sorry, of example problem that we're going to do. It's example 3.6. The difference between this one and 3.5 is that this one is thrown off the top of a building. It's still thrown at an angle, so we have to solve for the initial components. But some things are a little bit different since we have that initial height. Alright, to draw a picture, we have an initial velocity equaling 20.0 meters per second. We have an initial angle of 30.0 degrees. The height of our building is 45 meters. Okay. Remember that that will actually end up being a negative 45 meters because we are starting at the top of the building and the ball is going to land on the bottom ground. There are two things that we are looking for in this problem. A is the time of flight. And B, take a quick look here what B is. It is where does the stone strike the ground? So where does the stone strike the ground? What is that actually asking? Just like our other problems, they're asking for X, or the range. Now we may add a third step here and actually find the final velocity right before it strikes the ground, but we'll see when we get A and B done. All right, so the time of flight. The time of flight poses some problems for some students. The best way to do this is actually using the quadratic equation. Okay, so let's take a look at our equation of y equals VIYT plus 1/2 gravity times time squared. Are we going to be able to have an initial velocity in the y direction? Absolutely. Okay. Are we solving for time? Yes. Do we have y? Yes, we do. It's negative 45, and we know gravity. So we can use this equation, but as you can see, we have a t and a p squared. Okay. So before we put the numbers in there, let's go ahead and solve for VIX and VIY. I'm going to be restating some stuff from the other two example problems as far as the initial components. Our initial velocity is at an angle. Let me go back there for a second. VIX is in the x direction. VIY is in the y direction. After we solve for the components, we do not need VI. 20-degree angle in there. Oh, 30-degree angle. And as you can see, VIX will be the cosine because it is adjacent, and VIY will be using sine. I'm not going to go through and actually do the math there. You can go ahead and do that for yourself. If you need to refer back to 3.5 for that example on how to do that, that would be good. So the initial components are 17.3 meters per second in the x direction, and I believe 10.0 meters per second in the y direction. Both are going to be positive, and VIX should be bigger because it's only a 30-degree angle. Anything less than 45 degrees will have a larger x value than y value. Okay, so let's go ahead and plug in the stuff for part A using the quadratic equation. Y is negative 45. I'm going to leave out the units. If you take a look at all the units, we're all in meters and meters per second and seconds. So that's good. I'm going to drop the units for now, because for some of you that may be easier. VIY is 10.0 times the time, plus 1/2 of G is just negative 4.9 meters per second squared, times the time squared. Okay. I'm going to take 45 to the other side, so I would get 0 equals positive 45 plus 10t plus negative 4.9 t squared. This is perfect for the quadratic. So my negative 4.9 would be my A, my 10 would be my B, and my positive 45 would be my C. I'm not going to work through the quadratic, but remember it is negative B plus or minus the square root of B squared minus 4AC, all that divided by 2A. Okay. So you plug those numbers in. You're going to get one positive and one negative answer. And remember that time can never be a negative answer. So when you do this, that'd be time equals. Our time is going to be equal to 4.22 seconds. Okay. So that's one way of finding the time. Like I said earlier, some students do not like to use the quadratic equation. So I'm going to show you a second way of finding it. Finding the total time of flight. Second way. The easiest way, besides using the quadratic, would be to look at the final velocity in the y direction. Okay. So instead of explaining everything ahead of time, we're going to just work through it. First, we're going to find the final velocity in the y direction. I know the initial velocity, and I also know the y value. So if I use VFY squared equals VIY squared plus 2GY, I'll be able to solve for the final velocity. So that would be VFY is equal to square root of 10.0 meters per second squared plus 2 times negative 9.80 times negative 45. Remember the negative on the y. Now this calculation can be a little bit tricky. Make sure you use the correct order of operations for the square root. All right. So my final value for the y direction would be negative 31 0.3 meters per second. Okay. I'm gonna kind of box that here. Make sure you know where that's at. So now to find the total time of flight, it's fairly simple. We have the final velocity, we have the initial velocity, and we can solve for the total time. So we would go to the equation VFY equals VIY plus GT. You notice during the quadratic, I mean, it does look a little bit difficult, but if you do it the second way, you have to use multiple equations. So let's solve for the time. Time is VFY minus VIY divided by G. Now some students will attempt to just put the same values in for VIY and VIF, but that's similar to example 3.5 where you had ground to ground. You cannot do that anymore. The final velocity has to be bigger because it goes over a cliff, so it has more time to speed up. VFY, negative 31.3 meters per second, minus VIY, which is 10.0 meters per second. All that divided by negative 9.80 meters per second squared. And if we do it that way, believe it or not, we actually come out with the same exact value, 4.22 seconds. Okay, that will be the end of part 1 for example 3.6, okay, which involves throwing a stone over a cliff. In this part, we actually found time 2 different ways, okay, and that was part A of what they were asking for.